Hi everyone, welcome to Orgo Essentials, not your basic organic chemistry tutorial, Episode 6. In this episode, we'll talk about the Vesper Theory, learn the most common molecular geometries in organic chemistry, and go over some molecular shape practice problems. Let's get started. So far, we've been drawing 2D representations of molecules, Lewis structures, and discussing all the concepts that accompany them, formal charges and resonance. However, actual molecules aren't flat drawings, they're 3D. Because these three-dimensional shapes are quite complicated, there exist a few theories to explain them. The one we'll be covering today is called the Vesper Theory. Vesper stands for valence shell electron pair repulsion. This might sound complicated, but you already know what all of those words mean. A shell is an energy level that an atom's electrons are located in. The valence shell is the one the outermost electrons occupy, the one located farthest away from the nucleus. Next, an electron pair is simply what it sounds like, a pair of electrons that travel in the same energy level. Now, repulsion is the important word in this theory. Hopefully, you already know that electrons, because they all have the same negative charge, are repulsed by each other. In other words, they repel each other. Because of this, the main idea of the Vesper theory is that valence electron pairs will always be arranged in the way that most maximizes the distance between each other, the arrangement that most minimizes that repulsion. Like usual, minimal energy means a more stable compound. In this way, a molecule's geometry is determined. This sounds easy, right? Well, watch out. A molecule actually has two different geometries. First, we have the electron group geometry. This type of geometry doesn't differentiate between bonding electrons and lone pairs. It only counts the total number of electron groups in a molecule. For example, every compound with 4 electron groups is classified as tetrahedral, no matter how many of those groups are bonding, and if there are lone pairs on the central atom. The second type of geometry is called the molecular geometry, and this one does differentiate between bonding electrons and lone pairs. For example, though a molecule with a trigonal pyramidal molecular geometry and a molecule with bent molecular geometry both have 4 electron pairs, they have a different number of lone pairs on the central atom. Let's go over the first few basic geometries. Here is a summary chart of the geometries up through the first 4 electron groups. This might seem like a lot of information, but don't worry, we'll go over each row. First, we'll start with molecules with 2 electron groups. Molecules like this have 3 atoms, with bonding electrons in between those 2 side atoms. All molecules with 2 electron groups have what's called a linear electron group geometry. Any molecule with a linear electron group geometry also has a linear molecular geometry. For example, here are the Lewis structures for HCN and carbon dioxide, CO2. Though they have different arrangements of lone pairs, they each have both linear electron group geometries and linear molecular geometries. Note that whenever there are 0 lone pairs, the electron group geometry and the molecular geometry are the same. Also note that the bond angle for a linear molecular geometry is 180 degrees. There are 180 degrees between the 2 side atoms. Next, we'll move on to molecules with 3 electron groups. All molecules with this number of electron groups have a trigonal planar electron group geometry. There are 2 possible combinations for these molecules. First, there can be 3 bonding groups of electrons and 0 lone pairs. This means a trigonal planar molecular geometry. Remember that 0 lone pairs means the electron group geometry and the molecular geometry are the same. A molecule with a trigonal planar geometry, such as formaldehyde, CH2O, would have a bond angle of 120 degrees. As implied by the name planar, this molecule is flat. When a model is constructed, it can lay flat on a table. The second possible molecule with 3 total electron groups has 2 bonding pairs and 1 lone pair on the central atom. For example, sulfur dioxide. Though this molecule has 3 electron groups, just like formaldehyde, one of those groups is a lone pair on the sulfur atom. This lone pair repels the oxygen atoms with their many electrons, which pushes the molecular geometry to be bent or angular. This means that the bond angles will be less than 120 degrees. Finally, let's go to molecules with 4 total electron groups. All of these molecules have electron group geometries classified as tetrahedral. The first possible molecular geometry in this category occurs when all 4 of the molecule's electron groups are bonding, with no lone pairs. The molecular geometry for this will be, you guessed it, tetrahedral. An example of a molecule with this molecular geometry is our favorite methane, CH4. As you can see, every electron group is equally spaced out, with a bond angle of 109.5 degrees. The next possible molecular geometry with 4 electron groups is trigonal pyramidal. This molecular geometry occurs when there are 3 bonding electron groups and 1 lone pair on the central atom. Like with the bent molecular geometry, the lone pair on that central atom repels the bonding electrons, resulting in a smaller bond angle, about 107 degrees, most commonly shown as simply less than 109.5 degrees. One example of a trigonal pyramidal molecular geometry is ammonia, NH3. As you can see, the lone pair on that nitrogen atom is farther away from the bonding electrons. The final molecular geometry we'll cover today is actually one we already know, bent or angular. Though the names are the same, this geometry has a completely different look than the one present in sulfur dioxide. Let's look at water. In the Lewis structure, we can see 2 bonding groups connecting those hydrogen atoms, and 2 lone pairs on the central atom, oxygen. All those electrons crowded together have a lot of repulsive energy, leading to a bond angle of about 104 degrees, or less than 109.5 degrees. Again, here is a chart summarizing all of the molecular geometries up to bent. Although it can be useful to memorize all of this, it is not strictly necessary. If you ever need a reference, there are plenty of similar charts online and in textbooks. Let's do a few practice problems. First, let's predict the bond angles for ethylene, C2H4. The first step, like always, is to draw the Lewis structure. We know that the hydrogen atoms must be on the outside, that the carbons must have full octets, and that there are no charges on any atoms. So we can quickly draw the Lewis structure like this. Now, it might seem like there may be a problem. There's no one central atom. How are we supposed to figure out the bond angles? Fortunately, we can divide the molecule in 2, drawing a line down the center, like this. Now we can see that, on each side, carbon is a central atom, with 3 bonding groups branching off. There are no lone pairs. This means that the geometry is trigonal planar, which gives us bond angles of 120 degrees. Next, let's figure out the bond angles for acetaldehyde, CH3CHO. From the molecular formula and the name of the molecule, we can get a Lewis structure looking like this. Let's divide this into different sections. If we pretend that the oxygen and this hydrogen aren't there, we can see a tetrahedral shape, with 4 bonding pairs of electrons and no lone pairs. From our handy reference chart, we can see that a tetrahedral molecular geometry means 109.5 degree bond angles here, 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 and here. When we do the same for all the hydrogens on that central carbon, we can see a trigonal planar shape, with 3 bonding pairs and no lone pairs. A trigonal planar molecular geometry correlates to bond angles of 120 degrees here, here, and here. That's it for this video. Like usual, I've included a link to a document with some practice problems for anyone who wishes to get some more practice with molecular geometries. I've also included a reference table to be printed out for anyone who needs it. If you have any questions so far, feel free to email me or comment down below. Remember, practice only makes better. The next video will be about hybridization. I'll see you then.